Well, hello and welcome to the final video of week 6, a short video week this week. This week we're of course talking about discrete random variables and special situations which are known discrete random variables that have particular mathematics behind them. And today we're going to talk about the third and final one that we're going to investigate for discrete random variables, which is the Poisson distribution. Okay, so I'm just trying to make sure I stay in focus a little here. I got my Stitch shirt on, right? So little Disney all the time. You notice my Disney font, I guess up here. I like my Disney font. Hope it's readable. So the Poisson distribution is very different than the previous two we looked at. For geometric, we have a Bernoulli random variable, and we're counting how long it takes us to get our first success. There's one that's how long we take until we get multiple successes, like 3 successes, 4 successes. That's called hypergeometric. And there's the binomial distribution, which is how many successes we will get in a particular number of trials. And that's a very common one that we deal with all the time. But this one, the Poisson, is fairly different and easily recognizable from the other two. The Poisson is how many successes we see in a time period. So the number of trials is not known or even looked at. The number of times until we get our first trial is not what we're looking at. We're literally looking at, we have a certain period of time. It could be time. It could be distance. So my focus is going really bad today. It could be time. It could be distance. It could be area, right? And we're counting the number of successes. And usually the number of occurrences of anything is seen as a success. So for example, you might be at Walmart and you might say, what's the probability that in the first hour that Walmart is open that we see more than 100 customers walk through our door? Well, that turns out to be very much a Poisson distribution question. We might look at an arm and say, on a certain area of skin, what's the probability we see more than 5 moles, more than 10 moles, more than 20 moles? In today's skin cancer world, we're very concerned as people about moles that appear on our skin, and we need to learn to recognize them being cancerous or normal. And we also, as people, get concerned if we suddenly see an area that has a large volume of moles. So those can be Poisson distributions. One of my favorite Poisson distributions is if you drove a kilometer of highway, how many potholes do you hit, right? So theoretically, that is a Poisson distribution. Now, Poisson being loose in this case because it really is a theoretical situation. And Poisson doesn't really care about the probability of success or the probability of failure. It actually only requires the average number of successes for that interval. So if I wanted to do the Poisson Walmart question and say, what's the probability that I see more than 100 customers in my store in the first hour, then when we are given that question, we need to be told what the normal average is. So normally maybe Walmart sees 82 customers in the first hour, or more, maybe normally they see 132 customers in the first hour. So based on that knowledge, which comes omnipotently from some source, then what's the chance today we see over 100, right? And we might use this from a business perspective, determining how much staff we want on hand, right? So let's go to our board. And let's start off with just making sure that we recognize that we are talking about the Poisson distribution, which is, I just got to change my chair. I'm sitting a little wrong here, which is the number of occurrences of the success. So I'm writing it that way, but the number of occurrences of an event is another way to write that. In an interval. An interval is often time, distance, or area. Okay? And so if xi is that, then you could see that xi has the potential to be 0. Xi has the potential to be 1. Xi has the potential to be 2. And theoretically, xi could go up to infinity. So what's interesting here is that geometric could be 1, 2, 3 all the way up to infinity. Binomial could be 0, 1, 2 up to n, but Poisson is 0, 1, 2 all the way to infinity. So each of the 3 discrete random variable types that we look at have different possibilities for xi. And the formula for Poisson is P of xi is equal to e to the minus mu, mu to the xi, divided by xi factorial, where mu is the given average. So we actually have to be given the average to do this question. We're going to look at the end of this how we work out the average and standard deviation of each of these 3 distributions we're learning. We already did the one for general. It's those 2 formulas we have. And one thing I'll just say, it's on my mind right now. Remember that when we're dealing with data back in chapters 1, 2, 3, we have a formula for mu and standard deviation, one for population, one for sample. When we're dealing with discrete random variables, we have a new formula for mean and standard deviation. And now for these specific discrete random variables, we'll have 3 new sets of formulas. You have to recognize the situation and apply the right formula. You can't use adding up the numbers divided by 10 for a discrete random variable. It doesn't work. Okay. Now, this formula is complicated to calculate. E is a number. It's 2.17128, infinitely going like pi. Mu is given. You know, the power has a negative number. There's a factorial on the bottom. People don't love calculating this. And so for this particular one, we will really use tables. And I'm just going to open my table here. And my Poisson table, I'm going to throw that on this screen for you to see. Just give me a second. I got some buttons to click here, and then we click into this motion. So this is the PDF of Poisson that is given in your D2L. I do want to point out here that this Poisson uses lambda as the mean, okay? So it is lambda that is the mean in this situation. Let me just see if I can zoom in a bit here. There you go. Lambda is the mean. And I'm just going to move the title kind of out of the way for a minute. And the clock up there for a bit, and me over a tiny bit. Okay, so what happens in this situation is you look up lambda. So for example, suppose I said the average was normally 1 per hour. Well, the probability of 0 per hour is 0.369. The probability of 1 or less per hour is 0.7358. If I wanted the probability of exactly 1, I have to take 0.7358 and minus 0.3679. So I have to determine what I want from this situation. You'll notice a bunch of 1s for small probabilities, and those pewter out as we go to big probabilities. The means keep going over. So if I said, for example, let me go over here, and I said the average was 12. I normally see 12 per kilometer. What's the probability I see 11 or less per kilometer? So 11 or less, I'm going to highlight this whole cell. 11 or less under my 12 tells me that I have my 0.4616. That's 11 or less. And if I said between 6 and 11, including 6 and 11, then I would probably want to subtract off the numbers that are 5. So let me screen cap this a bit. Control print screen. And let me go back to my whiteboard. And I'll try to do this. This is going to involve a little looking at multiple screens. Right? So I'm going to just give me a sec here to delete some of this out of the way. And scroll. I've just got to look at my other monitor and see where you guys are seeing on here. Okay, so suppose for the Poisson question, I ask what's the probability that 3 is less than or equal to x is less than or equal to 11 if mu equals 6.5. So here, how do I want to do this? This is actually, for these type of questions, personally, I like to do this. And what I see in this situation is I want all the numbers 11 or lower. And I can calculate that on my table. So I want the probability x is less than or equal to 11. And for 6.5 less than or equal to 11 is 0.9661. Now, that is not what I want, though, because look at that. I want to stop at 3. So I'm actually looking for 3, 4, 5, 6, 7, 8, 9, 10, and 11. But my box includes this 0, 1, 2. So I need to get rid of this 0, 1, 2, which means I have to subtract the probability x is less than or equal to 2, which in this case, 2 would be 0.0430. Now, between my last videos, I went and got my calculator. I like a Dal Sharp calculator. So 0.9661 minus 0.0430. And it turns out that if the average is 6.5, there's a 92.31% chance that my answer would be between 3 and 11. This technique that I've shown you here works for any of our tables that have cumulative tables, geometric, binomial, and Poisson. And for geometric in D2L, I made my own table, which has one page of individual probabilities and one page of cumulative probabilities. For binomial, I uploaded 2 tables, one which is basic equal to probabilities and one which is cumulative. But actually for Poisson, cumulative is pretty much always the one that we are given, okay? And so it really is a matter of knowing what you're looking for and knowing what you're trying to do. Now, one thing I will mention about Poisson, the way that most questions get tricky is maybe I have a question that says the mean is 15 per hour. And then my question is what's the probability that x is less than or equal to 6 in sorry, I said if, but in a half hour. So because it's a half hour, my mean is 15 over 2. So 15 over 2 is 7.5. So therefore, the probability x is less than or equal to 6 under 7.5 is right here, 0.3782. And a common mistake, especially if you had multiple choice questions, a common mistake might be to look it up under mu is 15 and look at 6. And that's the wrong answer because your average that you're given has to be on the scale of the interval you're examining. All right, now I just need to get back here. Let me just open my previous one. Oh, wrong thing. Oh yeah, there's box. Don't save. And then there we go. Now I just need to scale this to where you guys see. Give me a second here to line this up for your visibility. I'm using multi-monitor shifting. That's good enough. There we go. Looks good. Okay. Now, our last topic that you read this week is for the mean and standard deviation. So remember, we have a geometric distribution which involved the probability of success P. We have a binomial distribution which involves N and P. And we have a Poisson distribution which actually is given mu. So if I want the mean of the geometric distribution, it turns out that the mean of the geometric distribution, mu, is equal to 1 over p. So we don't have to look at every possible values. If we tried to do this with the discrete random variable formula, we need to do it to infinity. Mathematicians have already proven that it's equal to 1 over mu. For the binomial distribution, it turns out the mean is equal to NP, where I'm using capital N. And don't forget that mean is also called expected value. So if I know that 25% of patients don't eat one meal every day in the hospital, and I ask for 100 patients' data, I expect to get 25 of them didn't eat one meal a day, right? So that's the expectation or the mean. And for Poisson, well, obviously, mu is the number that's given. For our standard deviation, we're going to look at actually variance because it's an easier formula. And the variance of the geometric sigma squared is equal to 1 minus p over p squared. So these are just straightforward formulas for calculating it. The variance for binomial is np times 1 minus p. And the variance is interesting here. The variance is also equal to mu. It turns out that the Poisson distribution has a variance equal to the mean. And then, of course, we would want the standard deviation. So I'm just going to make myself a little tiny bit more room here. Let me just pull this all up a tiny bit. So we would want the standard deviation. So standard deviation, sigma equals the square root of sigma squared with square root of that formula. Here, sigma is well known to be the square root of n onto p onto 1 minus p. So square root of sigma squared. And over here, sigma is equal to the square root of mu. So these are formulas that we should know. If you're thinking about constructing a formula sheet to have with you for testing purposes, quiz purposes, and exam purposes, that's a good idea. I don't provide one because with it being an online course, I want you to study by making those things. These are 3 sets of formulas that you should know. With those mean and standard deviation calculations, we could actually work out some of those things that we've done before. We could say, you know what? How much data is within 1 standard deviation of the mean? How much data is within 2 standard deviations of the mean? How much data is within 3 standard deviations of the mean? We could calculate all those things, and we could compare them to Chebyshev's rule, which they have to agree with because it's a hard, fast rule. But we could also compare them to the empirical rule. And that's a rule that says if our distribution is symmetric mounded, then we expect 68, 95, 99.7 to be our 3 numbers. And if we get numbers near that, then we might be, wow, this Poisson situation happens to be symmetric mounded. It usually isn't. This binomial situation happens to be symmetric mounded. The closer p is to a half, the more symmetric mounded it is. This geometric distribution happens to be symmetric mounded. And there might actually be some mounded nature to the geometric distribution that's not really though symmetric and things like that. So these are the things that we study in statistics. And this is really an important week because we now look at questions. So if I said to you, I'm going to have 100 patients come to my office today. How many of them do I expect to have serious medical complications? If I know from a national study that number is normally 12%, then that's binomial, the number that I'm looking at. If I'm looking at how many patients will I have enter my office until I get one with a serious complication, then that's geometric. And if I'm like, you know what, there's only 1 hour left of the day, I'd really like to go home early. How many patients do you think I will get in the next hour? That's Poisson. So these are situational occurrences of famous statistical distributions in our daily lives. Next week is our midterm week. So I will make a video about that, particularly to start week 7. But for now, just make sure that you're understanding the material we're going through, and don't be shy about contacting me for meetings or emails. Toodles.